Alrighty. I want us to start off our discussion of compounds uh, with this concept of Lewis dots. Okay. Um, Pardon me. If we remember from the beginning, compounds are pure substances, and they are held, which just means that they cannot be broken down by physical means. Okay. We can do a lot of chemistry with compounds, and we'll talk a lot about that this semester. Um, our compounds are held together by chemical bonds, and a huge chunk of Gen Chem 1 is figuring out what we mean by chemical bonds and how that works. Okay. Um, and so that's a big focus of what's coming. And all this is going to start with this idea of Lewis dots. Okay. This was put forth by a guy by the name of G.N. Lewis. G.N. Lewis is a very important person in terms of chemistry with contributions in bonding, thermodynamics, acid-base chemistry, spectroscopy, all kinds of fun stuff. And I just feel sad for him because he never won a Nobel Prize, but we talk about Lewis a lot. Okay, this is where we're going to get started. Okay, uh, the Lewis dot structure is a way for us to picture uh, the electrons available for bonding, right? These are the electrons, the valence electrons, right? We're going to picture the valence electrons and we're going to use it as a representation. So, for example, if we have a boron atom, we can draw the boron symbol. Know that boron being in group 3A has 3 valence electrons. So 1, 2, 3 dots on a boron. And we could do this in any way we see fit. 1, 2, 3, 1, 2, 3, etc. There's another way to do it too. I might as well draw all of them. 1, 2, 3. That's a B. Okay. Notice though, in all of these, we put 1 dot on each side. Okay, that's the way we're going to do this. 1 dot on each side before we start pairing them up. This is a lot like Hund's rule, right? One at a time, and then we can start pairing them up. If we look at, say, oxygen, oxygen is group 6A, so there's 6 valence electrons. 1, 2, 3, 4, 5, 6. Again, as long as you end up with 2 pairs and 2 singles, you're great, okay? There's no real way to get around that. Just to remind us a little bit, refresh our memory about um, valence electrons. Remember, the number of dots is the number of valence electrons. So we can get that from the group number, right? If you use the A or the B group numbering system. Um, for main group stuff, the number of dots is going to be the number of electrons that you lose to form an ionic compound. For nonmetals, this is going to be the number of electrons you have available to share. And we're going to get into all that stuff, right? The number of unpaired electrons will be the number of bonds that can be formed. So we're going to start getting into how we're going to form bonds and where things are going to happen as we do that, okay? Then we want to also keep in mind that as we're doing stuff, we can also do this for, as we're drawing Lewis dot structures, we can draw these also for ions as well. Remember, ions are going to gain electrons or lose electrons. And we're going to use this tool. So right now I'm just going to introduce the tool, but we're going to use this tool to come up with, to help us figure out how some compounds work and all that fun stuff. Okay, so let's look at some of this. Really, this is getting us into what we're calling the octet rule. So there's our number of, yeah, I should have switched this earlier. Number of dots, main group is how many electrons can be gained or lost. We can figure this out. For nonmetals, this is going to be how many bonds we can form. This is mainly for the unpaired things as we go. Remember, everything is trying to gain or lose to get to a stable noble gas configuration, okay? And all of that is isoelectronic. So we're going to gain, lose, or share. And depending on what kind of compound we're forming, gaining, losing, or sharing will work that out. So this is kind of, well, crap, that's not at all what I wanted to have happen. Okay, depending on what kind of compound we're talking about, gain, lose, or share will change stuff. Gain and lose is for ionic stuff, and sharing is for molecular stuff, and we'll get into all of that as we do it. If we're talking about ionic compounds and we're looking at Lewis dots, then we can add or remove dots to express this out for us, okay? So let's look at a fluorine atom. So if we have fluorine, fluorine's in group 7A, so we can give him 7 dots, 2, 3, 4, 5, 6, 7, okay? Because it's in group 7A, it's going to gain an electron. It's going to have 8 valence electrons. So we can turn this into an F minus ion by having 8 valence electrons there. We'll give it brackets and a charge, and that would be how we would do a fluoride ion. If we're looking at something like sodium, remember sodium has 1 valence electron because it's in group 1A. The sodium will lose that electron and become Na+. And so, interestingly enough, writing the sodium ion is the same thing as writing what its Lewis dot structure is, because if we lost electrons, we're not going to show any dots. But that's still the stable noble gas electron configuration for that. Okay. If we look at, say, selenium, okay, and I want to look at an Se2 minus, okay, so say this is our question, and we want to draw the Lewis dots for Se2 minus. Well, let's draw Se, okay, and then selenium's group 6, so 2, 3, 4, 5, 6. It's 2 minus, which means it's gained 2, so 1, 2 more. We have our 8, we're going to give it brackets, and now this is a 2 minus charge, so there we go. We're going to put these dots into practice relatively soon to look at how compounds are forming and all that fun stuff, but I want you to get a grasp on this and to remember where valence electrons come from and what they mean, okay? I will catch you later.